Hey, it's time. Good morning, everyone. For folks in the room and also viewing the seminar from webcast. Um, I'm Taozan with CARB Research Division. Welcome and thanks for coming to the today's seminar. So today's seminar, the topic is measuring emissions from the on-road vehicle fleet in West Los Angeles. Before we get started, I wanted to go over a few housekeeping details. We have a few exits, two in the back of the room and one in the front of the room. So in the event of a fire alarm, we're required to evacuate the room immediately. Please take your valuables and do not use the elevators. We will exit through the stairways and possibly to a relocation place across from the streets. Please obey all traffic rules while crossing the streets. If you need to use the drinking fountain or restroom, you will go outside the room, turn left, and then pass the glass sculpture, the Medusa's head or something like that, from the ceiling. Food service is also available in the first floor lobby. So with that, wanted to first do a few introductory slides to kind of give a context of the study. Here in California, we have quite a bit of monumental goals to achieve lying ahead, and primarily driven by the need to meet the national ambient air quality standards, particularly for PM and for ozone. And of course, we know light-duty vehicles are still a significant source of air pollutions. So we still, despite of significant improvement in our air qualities, we still have large areas in the states that are in non-attainment of the national ambient air quality standards. For example, the San Joaquin Valley and the South Coast Air Basin. And as an example, for South Coast, light-duty vehicles contributes about 20% of the NOx emissions in the year 2017. So light-duty vehicles is very important. And for that reason, it's important for us to continue to monitor light-duty vehicle emissions, especially under real-world driving conditions. And our speaker today has been doing that for a few decades, including several campaigns at a West Los Angeles location in the past 20 years. And we're going to hear from him about the latest campaign and historical record collected at that location. He's been using this data to analyze for a number of things, for example, to track fleet emission trends. And CARB staff has also have the opportunity to use this data to analyze a number of policy relevant topics. For example, we have used this data to look into the emission disparities for vehicles that are registered in socioeconomically disadvantaged communities versus those are registered in non-disadvantaged communities using the West LA data. And we have seen, as we can see in the graph on the right, quite a bit of disparities for the vehicles registered in those two kinds of communities. And wanted to mention that encouraged by that funding, we have actually proposed to our board a new research concept to use remote sensing measurements to collect vehicle emissions in multiple locations throughout the states. And our board has approved that research concept last December. So with that, I wanted to introduce today's speaker, Dr. Gary Bishop. He has been a research scientist with the Department of Chemistry and Biochemistry at the University of Denver since 1987. working with Professor Don Stanman and his group. The group has specialized in developing spectroscopic instrumentation capable of remotely detecting vehicle exhaust emissions. The group has used these instruments to measure light-duty vehicle fleets in more than 21 countries and in more than 30 United States locations. In addition, the group has used these instruments to measure heavy-duty diesel trucks and commercial aircraft in London, snowmobiles in Yellowstone National Park, and line haul locomotives in Nebraska. This work has resulted in 10 patents and more than 50 peer-reviewed journal publications. Dr. Gary Bishop holds a PhD degree in biophysical chemistry from the University of Colorado in Boulder. And without further ado, let's welcome today's speaker, Dr. Gary Bishop.
Thank you, Tal. Thanks, everybody. It's nice to be here. Denver's in a deep freeze right now, so it's kind of nice to come someplace and thaw out. So I'll start out by just acknowledging the support for this project from the California Air Resources Board, and can't do this without other people's help, and especially Caltrans for help. I had some permit snafus with this and had a couple of guys at Caltrans come through and help me straighten that out. And then I have to acknowledge my wife. You'll see later, she reads all the license plates, and that is not it's not easy, but it's terribly important, and she does a great job. So bear with me a little bit. I never know the audience I'm going to be talking to and what they're familiar with and what they know. So I thought to start out with, I just give you a brief history of vehicle remote sensing. And what many of you may not know is that vehicle remote sensing actually started with CARB. There was a 1973 project that Lockheed at the Palo Alto Research Laboratory undertook to build the first remote vehicle exhaust measuring system. They called it REMOVE. It was all analog. Everything was in the infrared. It was an infrared absorption spectrometer, much like the one I'm going to talk to you about a little bit later. It was battery powered. It had analog meters, and it worked sometimes for CO and HC. The results were never published, and all that ever existed from it is a report that's in the CARB library. And we found out about this maybe 5 or 6 years after we introduced our remote sensor. If you're interested in looking at that report, I actually scanned it and it's on my website. And it's quite interesting because about a third of the report goes into all the ways you could use a device like this to do inspection and maintenance, to do public relations, to do all types of fleet surveillance. All the same things that we talked about 20 or 30 years after this. This research project brought up a lot of these same things. So Don originally got the idea to do a remote vehicle sensor from a very small study by a guy named Cheney at the University of Michigan, when Don was at the University of Michigan. Cheney had put together what at that time was a high-speed carbon monoxide monitor. I think it ran at 1 hertz, which in the 70s was good. And Don told him, take it out and put it on a sidewalk on a street and see if he could see individual plumes from cars driving by. And he could. And he could see larger plumes when there were multiple cars and smaller plumes when there were single cars. And he wrote a small paper, and that was the original seed that Don got that you could possibly do this. And so in 1987, we built what we thought at the time was the first vehicle remote sensing system. It was only used the IR. It only measured CO and CO2. It used liquid nitrogen cooled detectors, and we could measure a car for CO, CO2 in a half second as they drove by on the road. General Motors demonstrated an instrument a couple of years later that looked a lot like the feed instrument that we had at the University of Denver. In 1990, liquid nitrogen was very unpopular with the general research community and especially engineers, and so we came up with a electrically cooled version that also added hydrocarbons. 1991, huge aircraft demonstrated one using an FTIR. They were ahead of their time again. The scan rate on the FTIR just was not fast enough for all applications, but they did demonstrate that it might be possible to use an FTIR to do this. The first commercial remote sensor showed up in 94. Hughes released their commercial sensor in 95. 1997, we upgraded our instrument to measure NO using dispersive spectrophotometers. That greatly improved our NO measurements. I skipped a step. We had a non-dispersive UV instrument that measured NO for a couple of years. It had terrible interferences with hydrocarbons. And so there were issues with high HC cars producing false positives. The dispersive spectrometer fixed all of that. In 2005, we upgraded with a second spectrometer, and we expanded the spectral range of the first, so that not only could we measure CO, CO2, and hydrocarbons in NO, but we could measure NO2, ammonia, and SO2. So starting in 05, we could measure NOx, which is very popular. And then the most recent development is a company in Tennessee called Heat has demonstrated and used an overhead device that uses tunable diode lasers in a reflective strip on the road. And so basically that's a quick overview. This is just a cartoon, but it's very illustrative for our instrument. I don't know how many of you have had absorption spectroscopy in college chemistry, but if you did, you probably used a Spec 20 at some point. Maybe even in high school you used one. It has a light source, it has a cell, and it has a detector. Very simple device. You shine light through the sample cell and your detector measures what comes through. In a nutshell, that's absorption spectroscopy for measuring vehicle emissions, except we cut the device in half. And we put the source on one side of the road, we put the detector on the other side of the road, and our cell is the roadway. Now, that brings on some issues. In the Spec 20, you know the path length that you're looking through because the cuvette is a certain width. And Beer's law says absorption is equal to concentration times a molar absorption factor and a path length. We never know the path length, and so that produces an issue, and I'll discuss that in a second. This gives you a better picture. Here's a picture of our source. I'll get into this later. It's currently IR and UV. The IR is a carbide gas clothes dryer igniter. Runs at 1500 degrees C, and you just plug it in. It's AC. It's hotter than anything you can buy for the laboratory. For our UV light, we use a xenon arc lamp, a very small one, 75 watts, but same type of lamp that they use in Hollywood for the big spotlights that they shine up in the sky, just a much smaller wattage. So this is what the detector side looks like. The white box there that I've labeled feet detector has all the infrared detectors, and it has mirrors and beam splitters that enable us to separate out IR and UV light. The two dispersive spectrometers are those rectangular boxes sitting on the ground behind it, and they're linked with a fiber optic cable that goes between the two. So all the UV absorption spectroscopy are done in the spectrometers, and the IR detectors are done in the white box. And then we also measure speed and acceleration. That's those bars on the left. They're just some parallel infrared light beams that we do a timing thing with. Front of the car to the front of the car, back of the car to the back of the car, do the math. We also take a picture of the license plate with the camera. This is what it looks like at the West LA site. It's an on-ramp from southbound La Brea Avenue to eastbound I-10. If you see the road barrel just behind the back end of the white car, that's where the camera is. There's a hole in the road barrel if you look real carefully. Early on, we had lots of problems with people stealing cameras. And Don came up with the idea to put it in a road barrel, and we haven't lost a camera since. Nobody pays any attention to it. But you can see the source is closest to us. All the detectors are on the other side. Cars drive by our sample cell. So how does it work? So feet is really a comparator. And what we do is we compare the measurements we get behind the car with measurements that we get from calibration cylinders where we have a known concentration of all the gases. Now, it can only measure ratios. Going back to the, we don't know the path length. If you remember that Beer's law equation, when you measure a ratio, you have a Beer's law equation for CO, for example, in the numerator, and a Beer's law equation for CO2 in the denominator. And since they're coming from the same tailpipe, from the same location, whatever the instrument sees, both of those gases are going to be well mixed coming out of the tailpipe, and they're going to have the same path length, and the path length cancels out. And so now we're left with a CO to CO2 ratio, or an HC to CO2 ratio, or NO to CO2 ratio. And it turns out that basically that's just a fuel-specific measurement for that car. And it's very simple without having to make any large assumptions other than the carbon fraction in the fuel, which is a very well-known quantity, to convert those ratios into grams per kilogram of fuel burned. And so most of the graphs that I show you today, that'll be the units that we'll be showing. And what that means is that if you see 10 grams of CO per kilogram of fuel, if that car operating in those conditions long enough to burn a kilogram of fuel, 10 grams of CO is going to come out of the tailpipe. Now, with those fuel-specific numbers, you can also do inventories. All you have to know is how much fuel is consumed in some area or by that car or whatever. And very simply, you can get total grams emitted from that much fuel. And so everything that we're coming from comes directly from the ratios. A lot of people will ask me the question, can we tell them any information about CO2? And the short answer is no, because CO2 in this case isn't an independent measurement. It's tied to measuring all the other pollutions. And so we don't have an independent measurement in terms of how much fuel that car is burning exactly at that time that we measure. All we know is the ratio of the pollutants. So I talked about it being infrared and UV and the spectrometers being connected by a fiber optic cable. And this is just a cutout view looking at the IR detector and one of the spectrometers. And so the light comes in from the light source, and actually there's duplicate optics in the source that are in the detector side, but the infrared and the UV light is imaged on top of itself. It comes in, it's focused down by a pickup mirror, but then it goes through a magic beam splitter. And why I say magic is because the material of this splitter and then the special coatings that they've put on this splitter make it so that 100% of the IR light gets transmitted through it and 100% of the UV light gets reflected. I have nothing to say other than it's just magic. And so we can separate out both of these spectral components and send them to the particular detectors that we need to send them to. And so there's 4 IR detectors. There's CO, CO2, hydrocarbons, and a reference channel. And then each of the spectrometers is just a standard grading spectrometer with a detector that we use to look at absorption spectra of the individual features. Here's a sample of what it looks like. So this is a half a second data behind the car. CO2 are the blue dots, and you can notice that they wiggle around. And that's the plume going in and out of the beam, or wider parts of the plume going in and out of the beam. If you look very carefully, the CO is the red triangles at the top. They wiggle too, but you'll notice that the reference is very flat and the HC looks very flat too. And I'll show you that. If you take those voltages that coming off the IR detectors and you apply the response curves that we have for each of those species, you get a concentration graph versus time that looks like this. And now you'll notice that all of these lines are wiggling around together, even the hydrocarbons. And it just so happens the hydrocarbon is the least sensitive measurement that we make. And the reason you couldn't see it in the voltage graph is because hydrocarbon sensitivities are on the millivolt level. Whereas carbon monoxide is probably on the hundreds of millivolt levels, and CO2 is on the volt level, to give you an idea of what the sensitivities are depending on the various species. Now, just to measure the ratio, we take those concentrations that we've calculated versus time, and then we plot them against each other, and you get a straight line. And you fit a least squares line through the straight line, and the slope of that line is the CO to CO2 ratio, or the HC to CO2 ratio, or the NO to CO2 ratio. And this is deliberate. This is an incredibly dirty car. And I did this because if I showed you a clean car, you wouldn't be able to see anything in any of the other graphs except CO2. And so grams of CO per kilogram of fuel are 550. You'll see later that the average at West LA now is 9 or 10. Hydrocarbons are, what was that, 14? Average at West LA is somewhere around 1. Now, the other thing that happens, and is much more prevalent today than it was back when we started, is that, well, what happens when a car goes by and all that's coming out of the tailpipe is CO2? Well, your ratios are all going to be 0. But for this type of instrument, a peculiar thing happens that unnerves people when they look at our data. And that is, our instrument will give you, if you measured a 0 100 times, it will give you a normal distribution around 0. That's averages 0. But it's going to have negative ratios and positive ratios. And there's nothing wrong with a negative slope. It's just that people start thinking about negative concentrations or negative fuel specific emissions, and it's not something they're used to seeing. Everything stops at 0. And this is just a couple of examples for CO and HC, what you see when you get a positive 0 and a negative 0. But this is really important. Because of that normal distribution, if we were to throw away the negative tail, it's not going to average 0. It's going to be biased high. And what it means is that when you see a negative 5 grams of CO per kilogram of fuel, it doesn't mean the car is cleaning the air. It's a 0 reading, but it also means that there's a 5 gram per kilogram of fuel measurement that is not 5 grams of CO per kilogram of fuel. It's also a 0 measurement. And so you'll see in some of my slides later on, there'll be negative tails in some of the distributions, and this is where the negatives come from, and the negatives have to be left in. Otherwise, you don't get a 0 reading, and you'll bias the means high. So I mentioned we do dispersive spectroscopy. On the IR side, it's all non-dispersive. The detectors just see heat. And it happens that the filters only allow heat to come through for the specific gases. But on the dispersive side, we actually take a regular spectrum. And this is spectra for NO, SO2, and ammonia off of off the detectors of what it looks like. And we just use classical least squares fitting techniques to fit the spectra to calculate the concentrations on the UV side. NO, SO2, and ammonia are between 200 and 226, in the very low range of the UV spectrum. But NO2 is much higher. It's up around 430 nanometers. And this is just what a standard NO2 spectrum looks like from behind cars. What you'll find out today, I'm mostly going to be talking about gasoline vehicles. There's no NO2 in gasoline vehicles, and so there's very little that I'll talk about in terms of NO2. NO2 is more applicable for diesels, and especially older diesels. I mentioned we get a picture. This is what the picture looks like. We get a license plate. This is what my wife sees. And I give her the emissions database, and she types the numbers in. And then I take the numbers, and I'll send them to Chris, who's back in the audience here, and I'll say, Chris, run these numbers for me. And he produces non-personal vehicle information for me to use. So things like make, model year, vehicle identification number, perhaps zip code of registration, things like that. Very useful for doing emission study, totally unuseful for tracking somebody down, which is not something we want to do. So today I'm specifically going to talk about measurements we make at this West Los Angeles site. I told you before, it's at La Brea Avenue and I-10. It's west of downtown. It's about halfway between downtown and Santa Monica on the 10 freeway, and it's traffic's going to the eastbound, and so going into town. To date, we started in 1999. We've collected 8 data sets at this location. 99 through 2005, the data sets were collected in the fall. 2008 to 2018, we started collecting the data sets in the spring. We've got more than 165,000 measurements for those 8 data sets. And the most recent was May of 2018, which will be one of the featured things today. One of the curious things in May, you never know what you're going to find when you go back and you do long-term studies. For some reason, traffic volumes in 2018 were down about 15% over the historical averages. I actually worked an extra day to try to get to the 20,000 matched measurements, and you'll see I didn't do that, but I came close. And I wasn't going to stay on Sunday, but stayed for Saturday. And this is not the only site that we've done this. There are at least 4 other sites: Denver, Chicago, Tulsa, and Phoenix. At least 4 other sites where we've got long-term measurements at. Phoenix stopped in 2007, but all the other ones are continuing even today. All these, anything I show you today, research papers, databases, reports, everything you can find on the website here. All the databases are public. If you want to download them and use them, have at it. Lots of other people have used our databases to support their research, and we fully support that. In fact, the website may be one of the best things that came out of this. And that was sort of just, I wanted to learn how to code HTML. That's how the website started. So, but it's been very useful. So we'll get into the data now. All of the particulars about the technologies are out of the way. So here are what the 8 data sets look like for carbon monoxide at West LA starting in 1999. The uncertainties are standard errors of the mean, and you'll see that since 1999, 20-year period, CO emissions are down 84% at this location. Now, this is in spite of the fact that between 2008 and 2013, the average age of this fleet went up 2 years because of the recession. It went from a 7-year-old fleet to a 9-year-old fleet. I held out hope that it would go down. I think it was 8.8 or 8.9 this year. I forget what it was. So it really hasn't moved since it went up. But you'll see why that age change hasn't made as huge a difference as it could have. But 84% is pretty good. And like I said, now we're down around 10 or 11 grams. It's a factor of 7 reduction almost over those 20 years. Here's what it looks like for hydrocarbons in NO. I'm just showing NO because I said we didn't start measuring NOx until 2008, whereas I've got NO measurements for every data set. And like I said, by and large, this is a light duty fleet. 1.5%, I'll show some of this later, is diesel. So it's generally a gasoline fleet. There's not a lot of NO2. And so the NO and the NOx numbers look very similar. You can see that HC is down almost 80%. NOx is down 76%. NOx is the one, or NO is the one that's trailing, and it's trailing because technology really didn't address those emissions until later, especially for CO and HC. They were much earlier, and I'll show that. So here's what the historical reductions look like on an age basis. So model years still overlap for some of these data sets, but not very well. So what I've done is I've taken the same aged vehicle. So in 2018, a 2019 is 0 years old, and a 2018 is 1 year old. 2, 3, 4, 5. So a 20-year-old car in 2018 is about a 1998 model year vehicle. Now in 1999, that 0-year car is a model year 2000, and a 20-year-old car is a 1980. So we're comparing totally different technologies here, but we are looking at just age effects on the fleet. And what you'll notice, of course, is that in 2018, for about the first 15 model years, the fleet averages don't change, which is not something that happened in 1999. You'll notice that really only the first 2 or 3 years of the fleet's age, the numbers you could argue are really close to zero, and then they start to go up quite quickly. Such that a 20-year-old car in 2018, that 1998, has a fleet average emissions that look a lot like 5 to 6-year-old cars did in 1999. Those are going to be 94, 95 model years. So they're both LEV 1s, but one's probably got a few pre-levs in there as well. Now, there are a lot of things going on here when you think about these changes. That 20-year-old fleet in 2018 doesn't have near the number of cars that it had when it was brand new. There's a lot of attrition going on here. So it's not just all deterioration. There's attrition going on that may be dampening emissions deterioration, as well as just emissions deterioration on average for those car fleets. I should point out, I wish PowerPoint worked in portrait mode, because I feel like landscape for science is really tough. And so I want you to see what the shapes look like for all 3 species, and it's really hard for me to do that and show it to you one at a time. So I put them all over on the left. You can't really read any of the numbers, but you can see how they change relative to one another, and then I'll focus in on them individually as I go through. So there's CO, here's hydrocarbons. As I said, the hydrocarbon detector is probably our least robust channel. There's a lot more noise, but you'll notice that basically the first 18 model years in 2018 have the same measurement. Essentially, these are all 0 measurements for 18 model years on hydrocarbons. It's just astounding, if you ask me. Hydrocarbons, and I'll show this later, is almost starting to become normally distributed. It's not quite. I don't think it'll ever get there, but it's awful close. You'll also notice that in 1999, there were more years that stayed close to that 0 range than we saw for CO, 4 or 5 years. But that number has tripled over that 20-year period. And you can see, especially for 20-year-old cars, and here again, the 19, 20, 21-year-old cars, if you average all of those, they're still working out to be somewhere around 6 to 7 years old in 1999 in terms of fleet averages. As I mentioned, NO hasn't gone down as fast as CO and HC, and that's in large part because NO wasn't really aggressively attacked until the LEV 2 vehicles came online. Full-time in 2009, they started to be phased in 2004, but I have no idea what the fractions were between those. I just know that by 2009, they were all LEV 2s. And what you'll notice is that the first 11 years in 2018 have essentially 0 readings. And it's much more striking. NO doesn't stay at 0 in 1999 at all. It goes up almost immediately. 20-year-old cars, this is the one species that you'll notice 24-year-old cars look like 24-year-old cars did in 1999. And that has to do with higher deterioration on the NO side, more than likely catalyst. But you'll notice that these LEV 2 vehicles haven't moved in 10 years. And so my guess is 10 years from now, the NO plot's going to look a lot like the HC plot. The first 20 years are going to, on fleet average, are going to have no emissions. How do the emissions distributions look? So this is a curious plot that you may not have run across. This is a cumulative probability plot that I've plotted based on a normal distribution on the x-axis. So if you look at the x-axis, you'll notice that it's not linear. Okay, it assumes a normal distribution. If the data were normally distributed, you'd get a straight line, a diagonal straight line. And of course, we don't expect the data to be normally distributed. But if I used like a log normal distribution, which would probably make more sense, I couldn't show you the negative tail because you can't take a log of a negative number. So I do it on a normal distribution so you can see the negative tail. So where that negative tail crosses zero basically is the length of that normal distribution. And you need to go that far to the positive side before the numbers are real, or non-zero would be the best way to say that. And what you'll notice is that in 1999, if you look at the 99th percentile, it's about a factor of 4 reduction. As you go higher in the distribution, that difference decreases. It's not as large. And the open symbols are the means for those two distributions. So in 1999, 10% of the fleet from this distribution was about 68% of the total emissions. In 2018, it's a little more than 90%. You get above the 99th percentile, and it's about a third of the emissions in 2018. And I forget off the top of my head what it was. But one of the curious things with CO is that there are still a few cars out there that go almost as high as they did in 1999. The frequency is much lower, but you still see a few. As I mentioned, the 99th percentiles dropped by a factor of 4. This was what it looks like using all of the years, all 8 data sets. And I've just played around with the fact, is it an exponential decay now, or is it still a straight line? And you can't argue anything but probably the straight line. Your eye says, oh, the exponential decay looks really good, but it's no better than the straight line. And so for a CO, it may still be going down at a quite significant rate. And this is kind of astounding if you think about it. The 99th percentile is populated by broken cars. All of these cars have something wrong with them. But somehow the manufacturers have figured out a way that when they fail, they don't go crazy like they used to 20 years ago. And somehow they're able to cap those emissions. And I'm sure it has to do with computers and fuel injection and all these things that they can control. But broken cars today are a lot less polluting than broken cars 20 years ago. And you see this for all the species. So here's what the distribution looks like for hydrocarbons. And as I told you, it's getting close to normal distribution. If you look at the negative tail for the 2018 data, that negative tail extends above the 90th percentile before you start having measurements that are significant. On the 10% basis, all the emissions for hydrocarbon in 2018 are above 90th percentile. Now I want to say above the 99th percentile, it's 45% or 48% for this set. And what you'll notice is that for hydrocarbons, the top of the distribution is still a factor of 2 lower at the very extreme, much more so than we saw for carbon monoxide. The shapes still look similar except at the bottom. Like I said, it's just being pushed down to 0. All these readings are zeros. And here's what it looks like for NO. As I said, NO started later, but you'll notice, just look at the difference between the 50th, the median, and the 90th percentile, how that portion has just been completely flattened out by all of the extra cars that are 0 or near 0 emissions for NO. I want to say in 1999, the 90th percentile and above was a little above 50, half of the NO emissions, and in 2018, it's 90%. It's just astounding. And here's what those numbers look like for the 99th percentile, looking at all 8 data sets. If we didn't have that first hydrocarbon measurements in 1999, you'd say that HC and NO are following the same line. But that first measurement, for some reason, was significantly larger than it was for subsequent years after that. But both, NO for sure is still coming down. HC may still be coming down some, but if you take that first point away and just look from 2008 and newer, it seems like the HC 99th percentile is just bouncing around the same number. Now I'm going to look at emissions deterioration. And I apologize, I should have put in a slide to explain to you how we do this, because it's probably not straightforward. But so I have 8 data sets. And so in 1999, we started measuring 1990 model year vehicles, and we measured them in 01, 03, 05, 08, 13, 15, and 18. If you take the mean emissions of the 1999 model year, for example, and you plot that against vehicle age, it goes 1, 2, 3, 5, whatever the rest of them are. And you assume that emissions deterioration is a linear process, and you fit a straight line to those points, you can calculate a deterioration rate in grams of pollutant per kilogram of fuel per year. And so that's what's plotted on the right-hand upper graph here for carbon monoxide. And it's also plotted for CO, HC, and NO. I've done this trick with all 3 on the left side of the axis again, so that you can get an idea of what the differences are. Now, one thing to consider is that not all of these deterioration rates start at year 0 or year 1, because in 1999, 1995 model year vehicles were already 4 years old. And so some model years start at an older age than others, and it has to do with just the timing, their model year and when we made the measurements. But we do that for each of these model years. We fit a straight line to each one of these, and then this is what it looks like for emissions deterioration by model year over this 20-year period. Now, keep in mind also, the uncertainties are the errors on the least squares fit. As you move to newer model years, we have fewer data points. And if you look at the bottom graph, which is a blow up between 2000 and 2013, you'll see that as you go to these newer model years, the uncertainties get larger. And that's because basically we're fitting 3 points to a straight line, which is the minimum that we have to have. And that's why it stops at 2013. That's the last model year that we have 3 data points to do this type of calculation. The other clue I'll give you is, if you look at the maximum here, it's around a little above 1%. If you look at that on a year-over-year change, that's about 7.5% per year on a rate change. And it turns out that all of these at their maximum are between 7 and 8% year over year, but they're different levels in terms of gram per kilogram, and it just has to do with the level, the mean emissions. The higher the mean emissions, the higher the deterioration is going to be for the same percentage change. So here's what it looks like for hydrocarbons. We talked about that first 20 model years, 15 to 20 not changing. You'll notice that by the time you get to 2000, you're at 20 model years. And if you assume that it goes forward just much like it does in the beginning, they don't deteriorate, which is why those average emissions don't change. And that's what we see here. Now, you'll see that they go down as they get older. This is likely an attrition effect. We can't prove that, but I'll make arguments that cars that have problems don't stay on the road as long as cars that don't. So that's conjecture on my part. I can't prove it, but that's one explanation. And then here's NO. And you'll notice that NO changes the most in terms of from the beginning to the maximum. And that, again, goes back to those mean emissions. You'll notice that after the first 9 or 10 model years, we started to see higher NO rates from the on-road fleets. And we also see that in the deterioration rates. NO going down at the end can have other causes, like rich operation. Car starts to run slightly rich based on stoichiometry. It doesn't make any NO. And so there may be competing factors in why the NO deteriorations go down. In 2008, we started measuring ammonia. And ammonia is, for some reason, the one species that's near and dear to me. And it may be because it's not regulated. And I think it's just kind of fun to look at the data. But so here are three measurement sets from 2008, 15, and 18. The uncertainties are standard errors of the mean. Ammonia is the only species that increases in emissions and then goes down. And the reason for that is that in order to make ammonia in a light duty car, you have to have a working catalytic converter, because the reduction reaction between NO to ammonia occurs on the catalyst. And when a catalyst loses its ability to reduce NO, it can't make ammonia. And so the ammonia goes away in the old cars. And you see that here, especially in the 2008 data. It peaks around 1993 model years and then goes down almost as low as we see for 1 and 2 year old model years. But what you'll notice as we go to newer data sets, that peak comes later and later. And it's easier to see in the next slide. Here I've plotted age again. So I've age normalized between all these data sets. And again, they're different technologies for the same age that we're comparing. But what you'll notice is that at least between 8 and 15, between 6 and 15-year-old cars, there's been quite a reduction in the amount of ammonia they produce. But it still goes up to about the same level. It takes it longer to get there in the newer data sets before you start to see it going down. And if you look carefully, in 2008, that peak is somewhere around 15 years old. In 15, it's somewhere between 16 and 18. And in 2018, it gets noisy. I'm running out of data when I get to 25-year-old cars. That peak is somewhere around 20 years old. What this is telling you is that catalytic converters are getting close to almost doubling their lifespan in a light-duty gasoline vehicle. Because without a functioning cat, you can't make ammonia. And now in 2018, they're lasting at least in 20-year-old vehicles on average, for fleet average. And that's astounding too. I think part of that has to do with fuel administration is so well controlled these days. A lot of time the catalyst doesn't have much to do, and that may improve its longevity. So one of the other things we did this study is we compared the 2018 measurements at La Brea to what IMFACT would predict for that exact fleet at La Brea. I'm not a modeler. California may regret that they put IMFACT on the web and anybody can go and click a few boxes and get numbers. But that's what I did. Here are the settings that I used on the right-hand side. I've used aggregated speeds because aggregated speeds will give me fuel consumption by model year. And I can use that to very easily convert IMFACT's tons per day into grams per kilogram. At La Brea, average speeds are about 20 miles an hour. So aggregate speeds are probably a little higher load than what we find at La Brea. But what you'll notice is that, this is gasoline only. I haven't done diesels. And what else did I do? It's only running exhaust. So there's no idling, there's no evaporative, there's no any sort of extra things. It's just tailpipe, which is all I'm measuring at La Brea. And what you'll notice is that it looks pretty good. There's very little CO emissions from 2004 and newer, and then they both start to go up. And of course, I run out of data long before IMFACT runs out of data. And so my uncertainties at the back end are absurd. And so you have to say, well, at the back end, they kind of agree because there's just too much uncertainty. And I've also shown you the different technology classes and where they've been phased in, this, that, and the other. So here's what it looks like for hydrocarbons. IMFACT produces total organic gases as grams of CH2. Feet produces grams per kilogram in grams of propane. And so I've had to convert my feet numbers from grams of propane to grams of CH2. So that's one additional conversion that I've done in this graph. But again, feet in IMFAC from 2004 and newer sees the same number, and then they start to go up, and I start to run out of data. The only one that shows any significant differences and perhaps a bias is for NO. You'll notice for 2009 and newer, the LEV2s, they're all zero. IMFAC carries that zero out to 2004 models. I don't know if that's a technology thing or whatever. At La Brea, that's where we start to see higher deterioration rates at 2006, 2007 model year. And of course, our numbers start to go up. And so there seems to be an underprediction at the back end between IMFAC and feet for gasoline only vehicles. I've got a couple of slides on diesels. 5 years ago, diesels were more interesting, but not much interesting anymore. But just to give you a historical trend at La Brea, there were more diesels back in the early 2000s than we see now. They've actually gone down. The only interruption of that decline was in 2013 when there were more light-duty diesels, the VWs and the Audis. But you'll notice that the age of the remaining diesels has gone up significantly. And some of that has to do with the recession, perhaps. But if you look back over the time, even in 1999, the diesel fleet was 8.3 years old. So it's only gone up a year from there. It's just that it got newer in the middle, and now it's gotten older again. If you look at the NOx emissions, you'll notice the fleets in 2018 is about 1.6% of the total that we see. And I have to point out, I'm only seeing low tailpipe diesels, okay? Any semis with elevated exhaust stacks are not included in this because I can't measure them because the exhaust isn't at the ground level. With that said, there aren't a lot of semis at La Brea, but there are a few. Our instrument got run over by one in 2013. But the point I want to make is about medium duty diesels at La Brea are about 1.5% of the fleet, but they're still about 10% of the NOx. Now, before 2008, all of those NOx numbers are composed solely of just NO measurements. They've been converted to NOx, but they don't have NO2. Whereas 2008 and newer, I have both NO and NO2 measurements. So those are true NOx measurements on the newer ones. If we look at these light and medium duty diesels by model year from 2018, this is what you see if you plot NO is in the gray bars. The fraction of the total NOx in NO as NO2 is in the gray bars. And then the open bars are just the concentration of NO2. What you'll notice is that prior to 2005, 6, 7, they average somewhere around 25 grams of NOx per kilogram of fuel. The newest cars and trucks, you'll see they're all below 5, and there are a few that are down around 2 or 2.5. One of the curious things on the light medium duty side is that we don't see reductions starting in 2009. We do see those in heavy duties the minute SCR systems started to come in. And I'm not quite sure. I don't know all the rules and the regulations, but we see that reduction start in 2010, when in my mind it probably should have started a year earlier. I'll point out the uncertainties again are standard errors of the mean. But what you'll notice is that certainly since 2013, those numbers have come way down from where they were. And it'd be interesting to follow those and see how. One of the questions about SCR systems to control NOx is what's their durability? How are they going to deteriorate? So we don't know. So in conclusion, we've completed our 8th data set at this West Los Angeles site. And as I pointed out, the historical reductions for all the major criteria pollutants are quite large and quite impressive, even though fleet age has gone up, which 20 years ago when fleet age went up, emissions automatically went up. One thing I didn't point out, if you looked at those graphs, take if you remember the HC graph in your head, how flat it was for the first 15 model years, we've depended on lowering fleet emissions by fleet turnover. You have a new lower emitting car that somebody buys and he replaces an older higher emitting car. Well, the median model year car at West LA is a 2011 or a 2012. And if fleet turnover follows normal statistics, the most likely car to be replaced is a median car. And so when the customer goes out and buys a 2019 today and replaces a 2012, you don't see any emissions reduction at all. It's just gone. You've got to get way back 20, 25 years old before you start to see reductions. Now, those reductions filter through because that 2012 doesn't get crushed. It gets handed down to somebody else at another used car lot. But that's a slower process than what it used to be. And so that's one of the things. Age is having less and less of an effect on fleet averages. 99 percentiles have decreased by factors of 3 to 1.5, depending on what species you look at. Ammonia emissions have only gone down about 14% since 2008, but catalyst lifetimes have gone up. And that's one of the reasons ammonia emissions haven't gone down much. Cars make ammonia longer now than they used to. The impact modeling, I think, was pretty successful. I mean, with what we have to work with. It's not an apples to apples comparison. It's actually quite good. NOx may be the only one that there seems to be maybe a bias. And NOx emissions from diesels have decreased about 40% since 2008, but they make up a very small fraction of the medium duty vehicles that you see at West LA. South Coast for years has had a campaign to not buy diesels. And so LA is unlike most other cities across the US in that the majority of their medium duty fleet is gasoline or CNG. And that's another reason why there are fewer diesels at the La Brea site. I've got lots of references in the back if you're interested. There are ones that are just specific to the West LA data, and then there are ones that just tell you how the remote sensing works and what we've done and other things. But I will stop there and take any questions anybody has.
Your picture of license plates was unreadable to us. Does your wife have particularly good eyes, or was there a better image for her?
No, the plate's clearly visible in the images that she gets to work with. When I first started doing this, nobody had any concern of what type of information I used or showed. That's changed over my 30 years. When we first started doing this in the early 90s, DMVs gave me everything: names, addresses, lien holders, just all kinds of information. Nothing I wanted, they just gave it to me. And license plates are technically public property, but privacy issues, I try not to display them, at least today.
I'll add one more question. With the Volkswagen cheating scandal, did that show up in your data?
Yes. If you go to, if you're interested, let's see which one. This third one, reactive nitrogen species emission trends in 3 light, medium duty United States fleets. I have a graph in there that shows mean NOx emissions for 2-liter light duty diesel engines, and show that the 2009 and newer 2-liter engines have the same average emissions as the 2005 and older diesel engines that had no emissions controls. I didn't name Volkswagen, but that graph, all those 2009 and newers are Volkswagens and Audis, the 2-liter engines. So yes.
I'll make one more comment. Hopefully one's not hogging the mic.
And I didn't show this. If you go to the report for this, I found 12 or 13 2009 and newer VWs and Audis between West LA, and I did measurements in Linwood the week before I did West LA, and 5 of those 12 or 6 of those 12, the characteristic, the telling sign of a VW diesel that's out of compliance is about 60% of the NOx is NO2. Unlike a standard diesel where it's 10 or 15%. These, because they had a catalyzed DPF, they made a lot of NO2. And so if you go to the report, there are still 4 or 5 that I saw in 2018 that were still the original engines on those VWs and Audis, because you can see the NO2 is just off the charts for those measurements. There aren't very many of them, but there were still a few. And I don't know, I thought they were supposed to be filtered out in California, but like I said, I found a few still. Sorry. And the report's on the website too, if you want to. I have no idea. Will it be on the website? Send you, will the slides be on the website?
The slides is already on the website, I think.
Okay. Yes.
Gary, background levels, do they affect your measurements at all, or changes, short-term or long-term changes?
The short answer is no, because what we do is we normalize from the air in front of the car to the air behind the car in all of the measurements. The same thing in the absorption spectroscopy. The reference is taken before. Now, background air can have short-term perturbations caused by other vehicles, and those sometimes can interfere. Occasionally, I will measure a Tesla, right? He gets filtered out in the end because he shows up as electric, and I go through and I say, that's not him, right? But if he's following a school bus, I'll measure something behind the Tesla. So.
Hi, Gary. Good presentation, as always. I just wanted to get your perspective, not on the gas phase, but on, particulate matter, and whether spectroscopic techniques like this will ever be able to do it. If you had an unlimited budget, or could you foresee any technological advances that would allow that?
Optical measurements of particles is a fool's errand, in my opinion. It's very hard, and there's nothing wrong. There are lots of optical particle measurements, especially on the ambient side, but they give you certain information, and it's not the same information that you'll get with any other particle measurement. And I'm not an expert in that. I took a class one time, and I had an expert in optical particle measurements talk about all the pitfalls of using those kinds of data. The difficulty you have to do behind cars, of course, is that road dust gets kicked up. And it can get entrained with the plume and look like it's correlated with the plume. And so you have to have ways to filter that out as well. Feet makes an opacity measurement, and I didn't talk about any of that. And it does work on soot particles, but it does not work. So we do it in the IR. One of the commercial instruments does it in the UV. That's a much better measurement, and they can see things like oil smoke and stuff like that. From a remote sensing point of view, my opinion is that you can come up with a device that will give you high emitters, but you probably cannot come up with a device that's going to give you a good zero measurement and therefore a good fleet average. Oh, do we have any from online?
Yes, we have a couple of questions from online audience. First one comes from Molly Hogan. Gary, great to hear your recent work. Cleaner cars. Cleaner cars are going to continue to make up the 99th percentile with the remaining vehicles closer to zero, which in turn reduces the overall emission measurement year averages. Is this process expected to be expedited with the use of alternative fuel vehicles, or deterioration rates show an increase in NO compared to the model work? Do you know to what extent models are trying to incorporate deterioration rates into their work?
Molly, you got to come to my CRC talk because I'm going to talk about electric cars and criteria pollutions. So the short answer on criteria pollutants is that it goes back to this fleet turnover issue. It's an easy sell to the public to say, I'm going to replace an internal combustion engine with a zero emission vehicle. Therefore, I'm going to get a lot of bang for my buck. But the problem is you're taking a zero emission vehicle, and in normal fleet turnover, you're replacing a near zero emission vehicle with it. And so you've got to get into, for example, off the top of my head, NOx in LA, which is what I'm going to talk about at CRC. If you replace the median vehicle, if you take 1,000 cars off the road, which is about 5% of the fleet at West LA, which is sort of one of the milestone points somebody's got, and the cars you take out average the median NOx emissions, you get a minus 0.3% reduction in NOx emissions for the whole fleet. If for some reason you can get them to average the mean, you'll reduce them equally. You'll get a 5% reduction. But it's difficult to get them to average the mean. You've got to replace 20-year-old cars with a zero emission vehicle, and those cars have got to go off the road. And so, irrespective of the fact that about half the fleet at La Brea are trucks, and right now, even though there are a lot of trucks that are promised, there aren't many SUV and trucks that are available in the all-electric side of the market. And so the chances of you even replacing the median vehicle right now, I think, is tough. And so you're looking at needing 50, 60, 70% of the fleet to be zero emission vehicles before you start to see significant reductions in some of these emissions distributions, because it's the distribution that matters. I forget what the last question, it had something to do with models, and she knows I don't know anything about models.
Second part of the question, deterioration rates shows an increase in NO compared to the model work. Do you know to what extent models are trying to incorporate deterioration rates into their work?
I do not. Although I'm going to talk about that at CRC too. Okay.
Next question comes from Jeff Long of CARB. Were you able to look at ammonia from diesels? Interested to see if you can see any ammonia slip with ACR.
Yes, there's a short answer, but it's not large. So Molly published a paper in 2019. It's not on my publication list, but it is on the website. It's diesel emission vehicles from heavy and medium duty fleets. It's in environmental science and technology. We show the ammonia measurements in there. I want to say 2011 and newer heavy duty diesel trucks average 0.18 grams of ammonia per kilogram of fuel, somewhere around 0.2. Now, pre-controlled diesels, that number is essentially zero. So there is an increase, but compared to light duty fleets, so in 2018, I want to say the mean at La Brea was 0.7. So there is some ammonia slip in the new diesel trucks. They do not emit ammonia at the levels we see from light duty vehicles, but there is some. And that paper goes into a little more detail if he's interested. And there should be a link to it on the website. I don't think it's come out of its quarantine yet, so you may have to go to ES&T to get it.
Next question comes from Sandeep Kishan with ERG. I think you've answered this, but did you see any changes in the light-duty diesel emissions by calendar year for the 2009 and beyond model year vehicles? These were the ones that were supposed to be taken off the road.
If you go to the report, there aren't many of them. I want to say it was 7 or 8 that I found in 2 weeks of measurements. So about, what did I do in 14? It's about 35,000 measurements or 38,000 measurements. I found 5 or 6 or 7, but half of those had high NO2 emissions. And so there were still a few, but not anything like, I want to say in 2013, just at La Brea, I found 100 light duty diesel vehicles in 2013, something like that. I had 400 across 3 cities. Still not a large number, but they stuck out. So hopefully that answers the question.
Thanks. So that's all the questions that we got so far from the online audience. Do you have any more questions from the audience in the room?
Thank you, everybody, for coming. I appreciate it.
Have you measured or studied operational effects through your remote sensing? And do you design your experiments to have low speed, constant flow?
So I did not cover that in this. It's also in the report. We do a number of comparisons with something called vehicle-specific power. And if you go to the report, what you'll see is that in 1999, vehicle-specific power had major effects on all 3 species. In 2018, it has almost no effect, at least over what we consider to be cycle VSP averages, -5 to 30. It's flat for CO and NO. HC still goes up with decels. And so you still see foot off the accelerator increases in fuel specific emissions, but not near as large as they were 20 years ago. The reason we work at on-ramps is because the car has to be burning fuel for me to measure it. And when you work at flat locations or downhill locations, so many cars today shut off fuel delivery when you go into a foot off coast, that we kind of waste our time in the sense that all these cars go by and they're not emitting even any CO2. So we've had to bias where we work. But I will say this in my defense. For whatever reason, the La Brea site is incredibly predictive of other places in the LA basin. It's that way for ammonia. There's a group at NOAA that did a plane study. I think it was a part of CalNext. My ammonia numbers matched the East Basin average that they, or the ammonia to CO ratio that they measured in the plane was what I measured at La Brea. For the West Basin, excuse me, the West Basin, non-dairy, just what they consider to be mostly dominated by cars. You look at my NOx and CO and hydrocarbon measurements. Ilana Pollock did a paper in 2010 that I highly recommend if you want to look one up, where she looked at 50-year trends in LA. And boy, my numbers at West LA look really good compared to the ambient measurements in her plots. And so there's something about that site that we got lucky.
Hi, great talk, thank you. So since you've done measurements in other cities, I'm wondering if you see any differences in fleet characteristics between the different cities.
Well, there's lots of fleet differences, okay? LA tends to be the oldest. It also has the highest percentage of hybrids, and it also has one of the lowest percentage of diesels. So Denver and Tulsa will have 3% of the fleet will be diesels. Most of those are going to be light duty pickup trucks. Chicago is the newest fleet. We chalk that up to road salt. They just don't last as long in Chicago, and so turnover is a little high. I want to say Chicago averages, even after the recession, 7 years old or 7.5 years old for a fleet average, and La Brea is 9. Denver's around 9. Tulsa tends to be between 7 and 8, depending on which year I go to. What else is different? We see the age. You see older cars in LA. 2015, I measured a 1932 coupe. And it was the real thing. It had CO emissions higher than the one I think I showed you on the graph from my sample on the thing. As far as emissions distributions, they look very similar. The frequency and the levels above 99% across all these cities look similar. And this is particularly interesting to me because Tulsa's never had an IM program. And so the fleets in Tulsa look a lot like they do in Denver and Chicago and Los Angeles. With some of these exceptions, aren't as many hybrids, there's more diesels, but you start looking at gasoline vehicles, they look very similar. They have a lot of the same characteristics. Any more?
We have one more question from online, from Scott Mason. Is your work in various areas, in your work in various areas, does any area stand out as a very good or bad for emissions? In other words, are the fleets that you tested similar or different? How does this affect mean emissions?
Well, one of the things I mentioned, I went to Linwood the week before we did West LA in 2018. And the very reason for that was Linwood was one of the first places we measured in LA back in 1989. And it had the highest CO and HC emissions we ever saw. And it also had the oldest fleet we'd ever seen. And so we went back 30 years later and we repeated that measurement. And Linwood looks a lot like West LA today. It's a little older. One of the fleets, I want to say, was 10.5 years old instead of 9 years old. But the emissions aren't significantly higher, and especially on a model year basis, they look very good. And ammonia measurements in Linwood, as in LA, we see catalyst converters lasting 15 plus years based on ammonia measurements. Linwood was the place that stood out. Linwood is a place, when we were first there in '89, we saw gasoline cars emitting black soot out the tailpipe like a diesel. And that's because I want to say we measured a car that was at 17.5% carbon monoxide. I don't know what that is on a gram per kilogram. It's got to be 1,400 or 1,500 grams of CO per kilogram of fuel. They quit running when you get close to 20% CO. And not because there's something wrong with the car. It just, there's so much fuel that won't ignite. And so that's the place that stood out the most. And it has cleaned up in large part like we see in all these other areas. And so that's a great story.
Okay, that's all the questions from online audience. Okay, if there's no more questions here, so we're gonna conclude our seminar today. Thanks for everyone for your participation, and let's thank our speaker again.